Okay, here's some problems on chapter 9. This is the chapter on conservation of linear momentum and center of mass. Okay, so question number 2. Okay, read through this, you hit pause. Okay, so basically you have two stones or two rocks dropped. Whoops. Okay, and this is a one-dimensional problem. Okay, so it's one-dimensional. So one rock is dropped, the other one's dropped on top of it. But to make my picture easier to see, I drew it like I did over here. Okay, so this is my y equals 0, positive directions down, right? And so at time equals 0, this one's dropped, okay, from rest, so v initial 0, okay, and m1 falls for 330 milliseconds. Number 2 is dropped a little bit later, okay, and they want to know that at 330 milliseconds, okay, after this one's fallen for 330 milliseconds, where's the center of mass, right there, where's the center of mass of the system, okay? So this picture here shows that number 2 is up here, okay, at that time. So everything in the problem is happening at the 330 milliseconds. But mass number 2 is only fallen for that much time, okay? So basically we need to know how far is number 1 fallen, how far is number 2 fallen, okay? So if I want to find the coordinate of the center of mass at time 330 milliseconds, okay, that's our general expression to find the y coordinate of the center of mass, okay? I go to each object's coordinate, multiply by its mass, divide by the total mass. Okay, so I need to find how far down each has fallen. So I use equation number 2 from kinematics, initial velocity is 0, acceleration is g. So I use that to find how far number 1 has fallen, and I use that to find out how far number 2 has fallen. Okay, so, and then what I did is they told me that mass 2 is 4 times mass 1. Okay, so if I call mass 1 m, I'm going to call mass 2 4m. That makes the algebra much nicer. Okay, so here I have m1, which is m, times my y coordinate. I have mass 2, which is 4m, times its y coordinate. Okay, I just wrote these in centimeters. It's nicer to write 9.6 centimeters than 0.096 meters. Okay. Now, actually, the other reason it's nice that I'm using centimeters is because I wouldn't want to have an m for meters here and an m for meter there because I'm already having m for mass. Okay. You could do it, but just make your m's look different. Okay, and then the bottom I have m1 plus m2, so that's m plus 4m, so I'd have 5m. Okay, so I do the algebra, and that gives me the coordinate of the center of mass. Okay, so 18.3 centimeters below. Okay, part B, they want to know how fast is the center of mass moving. So this center of mass, okay, has a velocity at the center of mass. Okay, and this expression looks just like that expression. Instead of adding up the locations in the masses, you're adding up the velocity in the masses. Okay, so I wrote that out here. Okay, m1, m2. So I had to find the velocity of each one. Well, I used equation number 1. Okay, initial velocity is 0, acceleration is g, and so the time for number 1, okay, everywhere I had a velocity, I put in gt. Okay, so time for number 1 is 330, time for number 2 is 140 milliseconds. Okay, so there's my mass m1, mass m2 is 4m, and the total mass is 5m. So the masses cancel, the m's cancel. Okay, and that gives me the speed of the center of mass. Okay, this is number 16. So read through this, hit pause. Okay, so there's two things going on. So I have this one, number 1 collides with number 2. Okay, that's this picture. So there's my before the collision, after the collision. So they stick together. So it's a completely inelastic collision. Right, kinetic energy is not conserved for the collision. Okay, so after they collide, okay, then they move off. Here's after the collision. Then they move off as one large block, m1 plus m2, and compress the spring. Okay, so let's do the collision first, because I'm trying to find how far is the spring compressed. Okay, so I need to find the speed at which they both move off together. Okay, so I conserve momentum. So my initial picture, remember momentum is mv. My initial picture, I have one moving. Final picture, that's why we need the pictures. Final picture shows they're stuck together, and they both move off with one common speed, big V. Okay, so I can get big V as a number. Done, because they give me the masses, and they give me the initial speed. Okay. After the collision, now they're stuck together. So instead of drawing them like this, I just drew them as one large block of mass m1 plus m2. So here's the before picture. Okay. This is before the spring is squished. Okay. This is after the spring is compressed. Okay. So the spring is compressed. Oops. I'll fix that. Okay. So the spring is compressed a distance d. Okay. So I want to find that distance d. Right. So here's our general energy expression. Oops. There's our general energy expression. Okay. Yeah, there's a normal force. Okay. But it doesn't do work because it's perpendicular to the displacement of the blocks. There's no energy lost to kinetic friction. Okay. The spring force is a conservative force, so the work done by the spring is wrapped up into the potential energy concept. Okay, so that's zero, energy is conserved. So my before picture is they're both moving with kinetic. Okay, so my reference point I'm putting here for gravity. Okay, so this thing's not moving up and down. So it's not that I'm ignoring gravitational potential energy, it's just that it doesn't change. Okay, so initial energy is kinetic, they're both moving. Initial energy, potential energy stored in the spring is 0. That's this point. Okay, it's not compressed yet. The final picture here, right here, is it's at rest momentarily, and all the energy is now stored in the spring. So K initial is that. Okay, and instead of writing M1 plus M2, okay, sometimes I can call it M12. That's what I did right there. Okay, makes the notation nicer. Okay, that's my initial kinetic. Final energy stored in the spring is 1/2 kd squared. Okay, and I already know V is a number from up here. Okay, so that tells me how much the spring is compressed. Okay, look at number 15. Put this one on pause. Come back. All right. So here's the collision. So here's my before picture. So the ball has initial velocity V0. Okay, hits the barrel. Okay, or the spring gun. Okay, the ball compresses the spring, and they both move off to the left. All right. So I'm going to conserve momentum for the collision. So initial momentum is the ball. Final momentum is they're stuck together and they're moving off to the left. So I can get capital V as a number. Okay. That's part A. Done. That's part A. Okay. Okay. Part B. What fraction of the initial kinetic energy of the ball is stored in the spring? Okay. Now, this is kind of like some of the other ones I think I talked about, where you're not going to find an equation in the book for fraction of kinetic energy. You have to figure that out. So what I did is I said, okay, let's say in my before picture, the ball comes in before it collides, has 100 joules of kinetic energy. Okay. After it compresses the spring, okay, the whole system is now moving to the left with 20 joules of kinetic energy. Okay. So 80% of kinetic energy, not 80%, well, 80% or 80 joules of kinetic energy is lost. Where did it go? Okay, well, it's now stored in the spring. So I have 80% of the initial kinetic energy is stored in the spring. Okay, but so they're asking for what fraction? Like, is it a half? Is it a quarter? Well, instead of 80%, the fraction is 0.8. Okay, well, how could you possibly get a 0.8 out of 120? Well, you do 100 minus 20, divide it by 100. That gives you 0.8. So what you did is you did K initial, there's your K initial, minus K final, divided by 100, which is K initial. So that's how you find the fraction. So the fraction of kinetic energy that remains, okay, not remains, the fraction of kinetic energy that's lost, meaning stored in the spring as potential, so I don't want to say it's lost, it's just converted into potential energy, okay, is my K initial, okay, that's just the ball coming in, okay. My K final is they're both stuck together, the ball and the spring gun, okay, and they move off with that speed, big V, which we have from part A, and I divide it by K initial, okay, all right, and then I just did some algebra. No, you can put in the numbers right here, but I just did some algebra. I just kind of simplified things. I got rid of the half. I divide it by little m, okay, I divide it by V0 squared, and I wind up with that expression. You don't have to do this. Okay, just now it's less math. Okay, so I have that number, I have that number. all right? And obviously that's a 1. And then you can see these, okay, all the units go away. I have mass on the top, mass on the bottom. Those units cancel. Speed squared on the top, speed squared on the bottom. So dimensionally it's correct. So that has no units. This whole thing has no units. Okay, so that says that 0.797, that's the fraction of kinetic energy that's now stored in the spring that the ball had. Okay, so that's what they're asking you to find. They ask you to find the percent. It would be 79.7% of the ball's initial kinetic energy is stored in the spring. Okay, this one, okay, I'm going to draw this before and after picture. Okay, this is number 13. So the bullet comes in, it goes through the block, and then the block flies up to some maximum, flies up to some maximum height, and then stops. So they want to know to what maximum height does the block fly up there. Okay, so first thing I got to do is I'm going to conserve momentum for the bullet and block collisions. Here's my before picture. Here's my after picture. Okay, so I did P initial equals P final for this system. Okay, so initially only the bullet has momentum. The final picture, you gotta be careful. Final picture, the bullet has already gone through the block. There's the final momentum of the bullet. And the block now begins to move with that speed, big V. Okay, so I have everything in here to get the final speed of the block as it heads up, as it's leaving the table. Okay, now after the collision, okay, so I want to know how high does the block go. Okay, now I don't care about the bullet. I already know the speed at which the block begins to move. That's that speed. Okay, now I want to know just how high it goes. So now it's just an energy problem. Okay, so E initial equals E final from there to there. So here's my reference point for potential energy. So initial energy is all kinetic, final energy all potential. Okay, and I'm using capital M, right, for the big block. Right, remember they're not stuck together. The bullet went through the block. Right, and I can just solve that for H. That's the height of the block. Okay, all right, so this one is number 9. Okay, number 9. So I had to go through a couple arguments here to figure out how to use the velocities given. Okay, so I have a space vehicle. They gave me the speed of the space vehicle with respect to the Earth. Okay, think of that as here's a person standing on the ground. Okay, it's like an airplane going by. Forget that it's in space. Okay, watch an airplane going by at that speed. And then this is the module, person in the module. Okay, that's the motor. Okay, then the motor detaches. Okay, that's this picture. Motor detaches, and the module heads to the right. Motor moves to the right. But they say the relative speed between the motor and the module is given like that. Okay, and they want to find the speed of the module relative to the person watching this happen. Okay, so what I did is, all right, so if you're standing here on the ground, plane goes by 100 miles an hour, that's the speed you measure for the plane. Okay, but let's say the motor breaks free, disengages, all right, and let's say this person on the ground says, I see the module go by at 100 miles an hour, but I see the engine kind of lagging behind it. It's only going at 90 miles an hour. Okay. Well, the person on the module says to me, the motor M1 is moving away from me at 10 miles an hour. Okay. So the velocity of the motor, velocity of number 1 with respect to the person in module M2 is 10 miles an hour away, minus 10 miles an hour. 10 miles an hour to the left. So this person says, I measure the velocity, okay, of the module relative to me, okay? I measure the velocity of the module relative to me as 100 minus 90. So it's V2, okay, that's what this person measured on the ground, minus V1, that's what the person measures for the other one with respect to the ground, okay? So that's how I'm arguing what that number is, okay? So I use the example of 100 miles an hour, 90 miles an hour. The relative difference between them is 10, okay? The relative difference between them here is 88 kilometers per hour. Okay, so here's my picture. Here's the before picture, okay? And again, there's a person on the ground. Don't worry about it being in space, okay? Again, you can think of this as like a car and maybe a trailer detaches from the car or something. All right. So here's the whole object. Right? And they tell you this is M1, and they tell you that the motor has 4 times the mass. Okay, so M1 and M2. So before picture, this thing has some speed. Okay. The after picture, the motor detaches. Okay. So the final speed of the module is V1. Final speed of the motor is V2. Okay. They want you to find V1, but they tell you that the velocity of the, go back here, the velocity of the motor, okay, with respect to the command module is, well, the relative speed between the motor and the command module is 88. So that means this person here sees this thing going away at 88 kilometers per hour to the left, okay? Just like this person sees this thing going away at 10. Okay, this person here sees the motor going away at 10. This person sees it going away at 88. Okay, so the velocity, or this is actually the speed, okay, because they give us 88. I don't care that it's negative. So the speed of the module relative, the speed of the motor, rocket motor, speed of number 2, relative to number 1, is, we got that from last time doing 100 minus 90, okay? So they gave that number to us as 88. So V relative, which is 88, is V1 minus V2. So I'm trying to find V1, all right? Okay, so I had too many unknowns. So now I conserve momentum for this. So here's my before picture. Initial momentum is they're both moving together. The final picture is, okay, and again, so it's this person on the ground who's conserving momentum. Okay, so this person looks and says, okay, the motor's still headed to the right. That's its momentum. The module, number 2, still headed to the right. Okay, I want to find V1, but I don't know V2. That's V2. So I just solve this for V2 right there. So bring V2 over and I get V1 minus V relative. So right here where I have V2, I put in V1 minus V relative. And then I have everything in here except for V1. And then what I did is, to do the algebra nicer, is they told me that if the module M1 is M, the engine, okay, the rocket motor 2 is 4 times M. Okay, so everywhere I have an M1, I put in M. Everywhere I have an M2, I put in 4M. So that gives me 5. So M1 is M, okay, and then M2 is 4M, and then do the algebra, solve this for V1, okay, just do the algebra, okay, solve for V1. My V initial, that's my 4600, my V relative is 88, okay, and that gives me the velocity of number 1, the command module.